Welcome to qnawire.
All right, so for problem number 47, an electron in a long organic molecule used in a dye laser behaves approximately like a particle in a box with a width of 4.18 nanometers. What is the wavelength of the photon emitted when the electron undergoes a transition from A, the first excited level, to the ground level, and B, from the second excited level to the... So to solve this, first we want to start off with equation 40.31 from the textbook. So E sub n is equal to n squared h squared over 8 ml squared. So the energy of a given level in a particle in a box. So now we need to calculate the transition energy for the transition from n equals 2 to n equals 1. So delta E is equal to E sub 2 minus E sub 1, which is equal to 2 squared h squared over 8 ml squared minus h squared over 8 ml squared, which is equal to 4 h squared over 8 ml squared minus h squared over 8 ml squared, which is just equal to 3E1. So it's going to be 3h squared over 8 ml squared, which is E1, so 3E1. Yeah. So now the energy of the photon emitted from this due to this transition is going to be equal to this change in energy. So the wavelength of a photon related to its energy is delta E, which will be the photon of the energy of that transition, is equal to hc over lambda. All right, which is equal to, I'll plug in this value, 3h squared over 8 ml squared. All right, so now we want to solve for lambda. Let's see here. So lambda is going to be equal to, let's see. So we got lambda is equal to, so we'll carry lambda over, bring this guy back over here. 8, I'll just work through this. So 8 ml squared hc divided by 3h squared. So that goes away, which is equal to 8 ml squared c over 3h. All right, so now we plugging in the known values that we're given, which is that L is equal to 4.18 times 10 to the minus 9 meters, and the mass of an electron is equal to 9.11 times 10 to the minus 31 kilograms, and H is equal to 6.626 times 10 to the minus 34 joule seconds. We can now solve for lambda is equal to 8 times 9.11 times 10 to the minus 31 kilograms. Oh, and C is equal to 3.0 times 10 to the 8th meters per second. Oops. Let's see here. Actually, to simplify this, let's do that. Give myself a little bit more room. All right, joule seconds. C is equal to 3.0 times 10 to the 8th meters per second. Meters per second. So let's come over here to give myself some more room. Lambda is equal to 8 times 9.11 times 10 to the minus 31 kilograms times 4.18 times 10 to the minus 9 meters. That's an 8. That's a 10 times 3.0 times 10 to the 8th meters per second. That's a 10. That's a squared times 3 times 6.626 times 10 to the minus 34 joule seconds. All right, so plugging all of this in, lambda is equal, so for the first transition from the first excited state to the ground state, is equal to 1.92 times 10 to the minus 5 meters, or 19.2 micrometers. All right, so now for the next step, we want to calculate the transition excited state from the second excited state to the first excited state. So that's going to be from n equals 3 to n equals 2. All right, so this delta E, I'll come up here, is equal to 3 squared h squared over 8 ml squared minus 2 squared h squared over 8 ml squared, which is going to be equal to 9h squared over 8 ml squared minus 4h squared over 8 ml squared, which is going to be equal to 5, that's not h bar, 5h squared over 8 ml squared, which is equal to 5 times E1. All right, that part's. So again, going back to using the lambda that we saw for in the previous expression, lambda is equal to 8 mcl squared over 5h this time. Which, to simplify this, sorry, I had to catch up myself on my notes. I got a little lost for a second. So to put this in the same make it similar to part A, we can see the relationship that 8/5 is just going to be equal to 3/5 times 8/3, which is mcl squared over h. So for the third to the second transition, from the second excited state to the first excited state, 3/5 of the wavelength from the first excited state to the ground state. So that's what this is here. So, because if you cancel that, you have 8/5. So 3/5 times 8/3. So this means that this lambda is equal to 3/5 times 19.2 micrometers. That's supposed to be a 9, which is equal to 11.5 micrometers. So it's a shorter wavelength for the transitions from the higher energies, which means higher energy, which makes sense.